In this video, we're going to dive a little more deeply into our function terminology. So we're going to define a couple of more concepts as regards functions. So remember that we have the generic setup f from our domain A. So A is here, and we call it our domain. And this goes into some space B, which we call the codomain, or target. In general, A is going to only fill up a smaller subset, and we'll call this f of A. And that's the image, of course. But what if I have a smaller set here, C? So I've got a set, and I'm going to call it C. A little script C. Well, I can also take the image of just the set, and I'll get a corresponding chunk in here called f of C. That is the image of C under F. And it's defined very similarly, right? So this is equal to the set of all B in B such that there's an A, there exists an A, backwards E means exists an A in A, or A in C now, sorry, A in C, such that f of A is equal to B. That's the definition. And I briefly spoke about this, but we can also talk about if I have a set in BV, right? So suppose this is B, and I have a set V. Then I can define the pre-image of V. So suppose this was A. And I'm going to call that set F inverse of V, right? Or F to the negative 1 of V. Actually, I don't really want to associate inverse yet because the inverse may not be even a well-defined thing. So this is just called the preimage of V in B. And it's equal to all A in A such that f of A lives in V. Right? So I basically invert this process. And we have a nice theorem which kind of brings together a bunch of different facts that are just useful as far as functions are concerned. So suppose we have f from A into B, and that u1, u2 subsets of A, v1, v2 subsets of B. Then we have the following things holding. Well, if u1 is a subset, so this little u here, this little leftwise u means subset. If u1 is a subset of u2, then f of u1 is a subset of f of u2. And that's pretty easy to see. How about B? If v1 is a subset of v2, then this is a little more tricky, but you can show this. Then f inverse of v1 is contained in f inverse of v2. Still not too bad, right? It mostly is making sense. C, for all sets U is a subset of f inverse of the image, so the preimage of the image of U. right? Equality may not hold. That's the whole thing there, but you know at least it's contained in there. And it's good to know that direction. And for all sets V, so U here was an A and V is in B, of course, otherwise this doesn't make sense. F of F inverse of V is contained in V. And the reason that's not necessarily equality is because V might have stuff that's outside of F of A, right? V might be strictly larger, and so of course I'm not going to get, if I take the pre-image of something, I'll get stuff in A, and so then I take the image of that, and I'll get stuff that's strictly in the image of A in the long run. E, F inverse of V complement, and I'll explain what this is equal to F inverse, basically this is everything not in V, is equal to, so the pre-image of the complement is equal to the complement of the pre-image. That's what that means, where V complement is equal to all the B such that B does not live in V. So that's a nice theorem. I'm not going to prove all these things. You can think about them, and they're useful to think about and to know. What's more important to know is the following definition. So a function is onto or surjective. So we call this function onto or surjective if f of a is equal to b. That is, I fill up b. So onto kind of makes sense, and surjective is kind of annoying that you just kind of have to memorize it. And a function is 1-to-1 or injective, another fun word, if for all, or if f of x equals f of y implies x is equal to y for all x, y in A. So that means that for every single point I have in A, then I'm going to assign a unique number in B. So no number is going to share the same function value with another point in A. And those are really useful. And so those are, because they're so useful, we're gonna give some examples of, you know, when all these things succeed and when all they fail, whenever they fail. So example, how about f of x is equal to cosine of x? So from R1 into R1. Well, what is that, right? Well, you draw the function, right? It's just the sinusoid. Sinusoid. So obviously it's not onto, because it's bounded between -1 and 1, always, right? Is it injective? So it's not onto, but it's also not 1-to-1. So sometimes we'll abbreviate 1-to-1 like this. And why is that? Well, it's periodic, so at every 2 pi, it reiterates itself. And so I'm going to have actually a lot of points going to the same point in the codomain. So how about f of x is equal to e of x? Well, it's not onto, because it's strictly positive. E to any number is positive. But it is 1-to-1. Right? Because I can always find a number If these two things are equal, then they have to be the same number, because I just take logarithms and then I get that they're both equal to each other, right? So it is 1 to 1. I know that much. And if you look at the graph, right, it's just the swoop going up, right? And if I draw any horizontal lines, there's exactly one point that horizontal line is going to touch. That's another hallmark of one-to-oneness. How about f of x is equal to x times x minus 1 times x plus 1. So this is a crazy function, but you should know how to graph things like this, right? So it's a third order polynomial. You know where its roots are, and so you graph it, right? So its roots are going to be at 0, -1, and 1, and you know that it's a cubic, so it's going to look roughly like this guy. Right, so that's roughly what the function looks like. Well, is this thing onto? It's certainly onto. It's certainly onto because every single number is going to be hit here, right? It ranges from -infinity to infinity and everything in between. In particular, it's continuous. So by saying that, I was implicitly invoking the intermediate value theorem, which is a useful theorem, but you don't have to worry about that right now. So it's onto, but it's not injective. Not 1 to 1. Because if I draw a horizontal line, I hit 2 points here. If I draw another horizontal line, I might hit 3 points. Right? So there's not a unique value associated to every single thing in the domain. How about f of x is equal to x cubed? Right? So the difference between this graph and this graph, right, the graph of this function, x cubed, is I don't dally in between. Here I just kind of swoop in and I swoop out. And so this will be onto and 1 to 1. Which is really nice. So we've got examples where everything succeeds and everything fails and everything in between.